NASA's Voyager 1 has just crossed the Heliopause, the true boundary where our sun's influence ends and interstellar space begins. After 45 years of traveling through the void, this tiny spacecraft has finally reached a place where the rules of our solar system no longer apply. But that's not the incredible part. What Voyager found there has left scientists stunned. Magnetic fields that shouldn't connect but somehow do. Plasma densities 40 times higher than our models predicted. And perhaps most astonishing of all, a region of space that isn't empty at all, but filled with structures and phenomena that could completely change our understanding of the barrier between star systems. These discoveries aren't just scientific curiosities. They're forcing us to rethink fundamental assumptions about how stars interact with the galaxy around them, and what truly defines the edge of a solar system. In this video, we'll explore what Voyager actually discovered at this cosmic boundary, why it's so unexpected, and what it means for the future of interstellar exploration. Voyager 1 launched on September 5, 1977, originally designed to study Jupiter and Saturn before their orbital alignment changed. Engineers expected it to last about 5 years. 45 years later, it's still sending data back to Earth. This spacecraft has traveled over 14.6 billion miles at speeds of approximately 38,000 miles per hour, making it the most distant human-made object in history. The same team of scientists and engineers who launched it have spent decades listening to its faint signals, maintaining a connection across billions of miles of empty space. The mission's primary objectives were completed by 1980, after Voyager sent back breathtaking images of Jupiter's Great Red Spot and discovered active volcanoes on Io. It went on to reveal Saturn's complex ring structure and the methane atmosphere of Titan. But even after these planetary encounters, Voyager kept going, entering the vast outer regions of our solar system. The heliopause marks where the solar wind, charged particles constantly streaming from our sun, finally gives way to the interstellar medium, the material that fills the space between stars. It's not a physical wall, but rather a transition zone where these two forces meet and balance each other. For decades, scientists could only theorize about what exists beyond this boundary. Would the magnetic field of the sun continue into interstellar space? Would cosmic radiation increase dramatically? Would there be a clear dividing line, or a gradual transition? The only way to know for sure was to send something through it. And that's exactly what happened when Voyager 1 crossed the heliopause in August 2012. On August 25, 2012, Voyager's instruments detected a sudden drop in the solar wind particles it had been measuring for decades. Simultaneously, its cosmic ray detector registered a sharp increase in galactic cosmic rays, high-energy particles from distant stars and galaxies. The signal took over 17 hours to reach Earth, traveling at the speed of light across 11 billion miles. When the data finally arrived at NASA's Jet Propulsion Laboratory in Pasadena, California, the readings were clear: Voyager had crossed the heliopause. Solar particles had dropped to nearly zero. Cosmic ray detections had increased by over 30%. These were exactly the changes scientists expected to see when crossing from the heliosphere to interstellar space. The team spent months verifying the data, checking and rechecking their calculations. They compared the readings with theoretical models developed over decades. They confirmed that Voyager had indeed left the protective bubble of our solar system and entered true interstellar space. But as scientists analyzed the data more carefully, they noticed something strange. Something that didn't fit any of their models. The first surprise was the magnetic field. According to every model, the magnetic field direction should have changed significantly when Voyager crossed the heliopause. Inside our solar system, the magnetic field is shaped by the sun. Outside, it should be shaped by the cumulative magnetic fields of nearby stars and the galaxy itself. Instead, Voyager detected almost no change in the magnetic field direction, only in its strength. This completely contradicts our understanding of how magnetic fields work at the edge of the solar system. Dr. Merav Ofer, who has studied heliophysics for over 20 years, was stunned. "It's as if the sun's magnetic field extends beyond its plasma bubble," she said. "We've been modeling this boundary for decades, and nothing in our calculations predicted this magnetic connection. Scientists initially thought it might be a coincidence. Perhaps the interstellar magnetic field just happened to align with the sun's field at that particular location. But that wouldn't explain why the alignment has persisted for years as Voyager continues its journey. Others suggested a temporary anomaly, but the consistent measurements don't support that either. Some even proposed exotic magnetic reconnection processes, but that would require energy sources not known to exist at the Heliopause. The data simply didn't fit any existing theory. But that was just the beginning of the mysteries Voyager uncovered. Even more surprising than the magnetic field anomaly was what Voyager discovered about the plasma density in interstellar space. For decades, scientists have believed that the space between stars is nearly empty, with just a few atoms per cubic centimeter. It's a cornerstone of our understanding of interstellar medium dynamics. But Voyager's measurements revealed plasma densities up to 40 times higher than predicted. The plasma wave instrument detected electron density readings that were dramatically different from what our models predicted. This isn't just a minor discrepancy. It challenges fundamental assumptions about the interstellar medium. If Voyager's measurements are correct, and after years of verification, scientists believe they are, then we need to rethink how material is distributed between star systems. This could affect everything from star formation theories to models of cosmic ray propagation. Some researchers now believe this might be evidence of interstellar material being piled up against the heliosphere, like snow against a plow. Others suggest it could be related to the local fluff, a cloud of higher density material our solar system is currently passing through. The truth is, we're in uncharted territory. Voyager is showing us a region of space no human has ever observed before. But the most astonishing discovery came when Voyager measured the structure of the Heliopause itself. The spacecraft detected a series of magnetic bubbles or cells at the boundary region, creating a foamy, turbulent zone rather than a smooth transition. This isn't just unexpected, it's revolutionary. For centuries, scientists have debated the nature of boundaries in space. From early astronomers who believed in crystalline spheres to modern-day researchers who model fluid dynamics at cosmic scales, this question has shaped our understanding of how star systems interact with their surroundings. Voyager's detection of this complex, cellular structure may have finally provided evidence that cosmic boundaries are far more dynamic and structured than we ever imagined. According to Dr. James Drake, plasma physicist at the University of Maryland, this is the kind of discovery you hope for but never expect. It suggests the Heliopause isn't a simple boundary but a complex, active region with its own unique physics. It will take years to fully understand the implications. These magnetic bubbles appear to be created by a process called magnetic reconnection, where magnetic field lines break and reconnect in new configurations. This process releases energy and creates these distinct cellular structures. On the Sun, magnetic reconnection causes solar flares. At the Heliopause, it appears to create a foamy boundary that mediates the interaction between our star and the galaxy. What makes this particularly significant is that these structures create pockets where solar and interstellar material can mix in ways previously thought impossible. They may even allow some solar particles to leak into interstellar space, extending the Sun's influence beyond what we considered its absolute boundary. Beyond the scientific wonder, these discoveries have practical implications for future space travel. Currently, radiation shielding requirements prevent us from sending humans on long-duration missions beyond the Moon. Voyager's measurements of how cosmic rays behave at and beyond the heliopause suggest that radiation might not increase as dramatically as feared in some regions. This could revolutionize how we approach radiation protection for deep space missions. Engineers at NASA and private space companies are already incorporating Voyager's data into designs for advanced shielding systems. While practical applications are likely decades away, the theoretical groundwork is being laid now. The discovery of the magnetic bubble structure also suggests potential pathways of lower radiation that future spacecraft might navigate. Think of them as interstellar shipping lanes, where cosmic ray intensity might be naturally lower due to these magnetic structures. As Dr. Kathleen Mant from Johns Hopkins Applied Physics Laboratory explains, understanding the fine structure of the heliopause isn't just academic. It could literally map the safest routes for future interstellar missions. This isn't just about understanding the universe, it's about what we can do with that understanding. Voyager 1 continues its journey into interstellar space, now 14.6 billion miles from Earth and traveling at 38,000 miles per hour. But the spacecraft faces significant challenges. Its power source, a radioisotope thermoelectric generator, produces about 249 watts, down from 470 watts at launch. Engineers have shut down non-essential systems to conserve energy. The spacecraft communicates with Earth using a 23-watt transmitter, about the same power as a refrigerator light bulb. By the time that signal reaches Earth, it's so faint that it requires the world's most sensitive radio antennas to detect it. The Deep Space Network uses 70-meter dishes to capture these whispers from the edge of interstellar space. NASA expects Voyager to continue transmitting data until approximately 2025, when power levels will become too low to operate its remaining instruments. Until then, it will continue sending back measurements from regions of space no other spacecraft has visited. The data rate is painfully slow by modern standards, 160 bits per second, thousands of times slower than even the most basic internet connection. Each image or complex measurement must be carefully compressed and transmitted over hours or days. But every bit of that data is precious, offering insights available nowhere else. Even after Voyager falls silent, its journey will continue. In approximately 40,000 years, it will pass within 1.6 light-years of the star Gliese 445. In 296,000 years, it will pass Sirius, the brightest star in our night sky. And it carries the golden record, a message from humanity that will outlast Earth itself. Long after our civilization is gone, Voyager will still be traveling among the stars, carrying evidence that we were here, that we explored, that we reached beyond our world. Voyager's discoveries have inspired plans for a dedicated interstellar boundary explorer mission. NASA is developing concepts for the Interstellar Mapping and Acceleration Probe, IMAP, a spacecraft specifically designed to study the heliosphere and its boundary regions. Unlike Voyager, which was equipped with 1970s technology, this new mission would carry advanced particle detectors and magnetometers capable of mapping the complex structure of the heliopause in unprecedented detail. This mission could answer questions Voyager raised about magnetic field alignment, plasma density anomalies, and the bubble-like structure of the boundary. It could map the entire heliopause, not just the single point Voyager passed through, and measure particle acceleration processes that Voyager's instruments couldn't detect. If approved for full funding, IMAP could launch as early as 2025. While it won't travel as far as Voyager, it will provide a more complete picture of the solar system's boundary. But until then, Voyager remains our only direct window into interstellar space. In the meantime, we can marvel at what Voyager has already accomplished. A 1,820-pound spacecraft built with 1970s technology has traveled farther than any object in human history. It has shown us the outer planets in unprecedented detail. It has sampled the space between stars. And it has challenged our fundamental understanding of the cosmos. Voyager's primary computer has only 69.63 kilobytes of memory, about 15,000 times less than an average smartphone. Its camera, now deactivated to save power, was less capable than the front-facing camera on a budget phone. Yet with these limited tools, it has made discoveries that the most sophisticated Earth-based observatories couldn't make. Voyager reminds us that exploration isn't just about technology, it's about human curiosity. The same drive that sent our ancestors across oceans and continents now propels our machines across the solar system and beyond. Each boundary we cross reveals new mysteries, new questions, new frontiers. The team that built and operates Voyager spans generations. Engineers who worked on its launch are now retired, having passed their knowledge to younger scientists who continue to extract meaning from its faint signals. Some team members weren't even born when Voyager left Earth. Yet they all share in humanity's greatest journey of exploration. The edge of the solar system isn't where our sun's light ends or where its planets cease to orbit. As Voyager has shown us, it's where our understanding begins to transform. Beyond that edge lies not emptiness, but a universe more complex, more dynamic, and more mysterious than we ever imagined. And Voyager 1, humanity's most distant messenger, continues to lead the way, one bit of data at a time. If you've enjoyed this exploration of Voyager's discoveries, please consider subscribing to our channel for more videos about space exploration and the mysteries of our universe. And let us know in the comments, what do you find most fascinating about Voyager's journey beyond the solar system? Until next time, keep looking up, and out.